We are given a thin spherical shell of radius r and surface mass density of sigma units per unit area. In SI units, sigma kilograms per square meter. That's a mass density, but it's a surface mass density. Question is, about an axis of symmetry, what is its moment of inertia? Now let's say we know that the moment of inertia for a solid sphere is 2 by 5 mr squared. Can we find the moment of inertia of this from this formula? It's pretty straightforward. Let's start by writing it in terms of the density for the solid sphere. It's going to be 2 by 5. The mass of a solid sphere is going to be its volume 4 pi by 3 r cube times density, that's the mass, times r squared. That's going to be 8 pi by 15 r to the power of 5 times rho. Now we're going to create this thin shell by letting the radius r increase by a small, that is an infinitesimal amount, dr. This is the moment of inertia for a sphere of radius r, a solid sphere. If I increase the radius by dr, the increase in the moment of inertia will be the moment of inertia of the thin shell. Now di is going to be simply di by dr times dr. Let's do that. Let's take I and differentiate it. So we have di is equal to derivative of this, which is 8 pi by 15 times 5r to the power of 4 times rho dr. This increase in the moment of inertia is the moment of inertia of this shell. But there is a little problem. We have been given a thin shell whose area density has been given, but here I have the answer in terms of the volume density. How do we go from volume density to area density? That's very simple. Consider this thin shell. Its volume is 4 pi r squared dr, and the amount of mass it has out there is this volume multiplied by the density. That is equal to mass per unit area times the surface area, 4 pi r squared. 4 pi r squared cancels, and you get sigma is equal to rho dr. So out here we can substitute sigma for rho dr, and we get 8 pi by 3 r power 4 sigma. That's the moment of inertia of a thin shell. Let's verify this by integration. So first, what we do is we take this horizontal plane, and in that we set up our x and y coordinates. Let's say this is the x-axis, and let's consider a radius which makes an angle theta with the z-axis. The z-axis is the axis about which we want the moment of inertia. Let this angle be theta. So what we are going to do is we are going to cut up this shell, this thin shell, into thin circular strips like so. And if you look at this thin circular strip, its width is nothing but r d theta, and its length is r sine theta is the radius. So its length is 2 pi r sine theta times r d theta is the area of this strip. So the amount of mass there is out here is times sigma, and this can be treated as a ring, and the moment of inertia of a ring is mass times square of its radius about the central axis. The radius is r sine theta, so r squared sine squared theta. This is the moment of inertia of this ring, and we just have to add the moments of inertia of all the rings, which is we need to integrate this theta going from 0 all the way down here to pi. First, pause the video and see if you can do the integral. Let's see what all come outside. 2 pi sigma r squared r to the power of 4 come outside, and then inside you have sine cube theta d theta from 0 to pi. Sine cube theta d theta can be written as sine theta d theta times sine squared theta, which is 1 minus cos squared theta. If I put cos theta as z, this becomes 1 minus z squared. Sine theta d theta is derivative of cos theta with a minus sign. So minus dz. So I'll let you finish this integral and substitute the limits, and finally you'll get the same answer, 8 pi by 3 r to the power of 4 sigma.